Welcome to Astronomy Overview, where we're going to the next part of learning about our remarkable cosmos. We'll be focusing on our star and our closest neighbor to Earth, which is the Moon. After that, our next lesson will be over the planets that make up our solar system, some of the things that exist beyond our planetary boundaries, because our solar system is enormous. But when you compare it to what space is, it's just little bitty. But to really grasp how big our solar system is, we just got to kind of start with our sun, learn about what it does, some of the remarkable things and how it operates and why it's so important to even us on planet Earth. So let's start with that aspect and investigate the sun. And I want to link something to our last lesson. You might have noticed I emphasized a word a lot in the last lesson: supernova. Well, supernovas are important because they're the representation of exploding an old star, and the explosion of that old star provides the necessary brew, the ingredients to make a new star. Our sun is no different. So not all stars are the same age. Some are very, very old. In fact, some are just not even there anymore in outer space. We're just still seeing their light. They've exploded a long time ago. But our sun is actively alive in terms of producing its energy. We know it started to form around 4.6 billion years ago. When a sun is being made, it is a process by which the gases begin to come together, and then over time it starts to make fusion. Well, our sun has been doing that for at least 4.6 billion years. In the early existence of the sun, lots of the debris that was coming together got blown out. So that included heavier elements such as iron and nickel, other metals, and then some of our gases like helium and hydrogen, nitrogen, and they got blown away. And some of the lighter elements in higher concentrations traveled further into our solar system. And that'll be important when we link that up to how our planets were made. But we need to think about just our sun being a main sequence star, how important that is, because we are one of around 200 billion, that's B as in Bravo, suns, stars that exist in just this one galaxy called the Milky Way. So we have one sun in our solar system, and some solar systems that can have binary systems. So we're kind of cool that we just have one, and our sun is huge. It's about 1.4 million kilometers in diameter. So it's larger than anything else in our solar system. It will change to the red giant stage. So we learned about those different stages of a star in our last lesson, somewhere around 5 billion years from now. So I don't think we have anything to worry about in terms of our sun disappearing anytime in human reference. So the composition of our sun is pretty cool. We have 74% made up of hydrogen. That's an important element because that and the helium, and that makes up 24%. They make up a majority of what happens in our sun, what it's composed of, but it still has some other trace elements and other things that make it up, including some of the metals, carbon, oxygen, neon, some things that we think of. And those are important elements because they do, and some of these other elements blew away from the sun early in its existence. So its hottest part is much like planet Earth. Its hottest part is in its core because that's where we have our fusion happening in the sun. Without the fusion, the sun would begin to die. And you know the stages of the sun where that would happen. Right now, it's estimated that our core is around 15 million degrees Celsius. That is just incomprehensible to me. And its surface exists around 5,500 degrees Celsius. So The outer atmosphere of the sun is an important element because it's actually hotter than the surface by a few million degrees, and we'll talk about why shortly. So, investigating the core in more depth, we're looking at the nuclear fission action item. It's the place where the goods happen that make the sun what it is today. So what happens is the nuclear reactions consume our hydrogen to form helium, and that nuclear fission is what creates the heat that we have in our sun. The radiative zone of the sun extends from the outer edge of our core to the base of the convection zone, which we'll cover in just a second. This area is so important because it transports the energy that comes from that nuclear fission and moves that core upward. So our Earth isn't too different except that we don't form nuclear fission. We just have an iron nickel core, but we kind of have that same convection state that happens, but the radiative zone is important for making that next section occur. So it's actually helping to transport some of that heat, most of that heat, from the nuclear fission upwards through the sun. In the convection zone, this is the uppermost layer of the sun's insides, or its interior, and it extends from a depth of 200,000 kilometers. Wow, that's so much bigger than our planet Earth is. It makes me marvel at the size of the sun. So the motion of the convection zone is seen when we can look at the sun through telescopes, and please don't be looking at the sun with your just bare eyes. You can actually do serious damage and lead to blindness by doing that, especially something like an eclipse. So be careful, because the sun has lots of radiation that you can't see with your regular eyes, but it still can be damaging. But when we investigate the sun with telescopes and so forth, then we can actually see that there's these granular spots on the sun, and it gives the sun almost like this grainy looking texture. So it's not smooth. It doesn't have a smooth appearance. So let's talk about the sun's exterior. We learned about the three main parts of the insides. Let's look at the exterior and show you what happens there. The photosphere is the visible surface that we see of the sun, and it's the lowest layer of its atmosphere, or its exterior. These are where those granules actually hang out. That's where they set. And this is a majority of where the sun's energy gets emitted to outer space. So we've moved that energy from the core, and we've gotten it up to the convection zone, and then we get it up to the first layer of the exterior and the photosphere, and that's where we can begin to release our energy. Moving up to the top layer of the sun, its outer section is the chromosphere, and we're going to have a section that radiates energy beyond that it's atmosphere, but this is the exterior, if you want to call it, skin or outer layer of the sun. And we do see an increase in temperature here from what we saw in the photosphere. It can get from 6,000 degrees Celsius up to 20,000 degrees C. And there's some reasons for that, but this is the layer right here, the chromosphere, and it's a very irregular shaped item. So let's talk about the atmosphere of the sun, which is the corona. And this is about 200 times hotter than the photosphere. So it is very, very hot, and it's very thin. It extends outward. It's a faint part of the sun. This is actually an important part of what you might see during a total or partial annular eclipse of the sun. We can see the sun with special telescopes like a coronagraph, but you and I can't physically see the corona. Maybe if we were in an eclipse situation, obviously with the right protective gear on, but we would be able to see those outer faint layers of the atmosphere. Otherwise, you and I, just with our visible eye, that's not something you and I are going to see. But keep in mind that corona, the atmosphere, is just incredibly hotter than anything at the surface of the sun, and making it a very important part of it. So let's talk about how we release or use energy at the sun's surface. So the sun has this energy that it creates, and as it is producing it, we get charged particles along its surface known as plasma that get supercharged, and then they start heating up, and the temperature of this plasma gets so hot that the sun's gravity can no longer hold on to it. So it pushes that energy out in the form of solar wind. Solar wind is so important to us here on planet Earth, and we'll learn a little bit more in today's lesson about why. So as the energy travels along the sun's magnetic field lines, eventually it finds a way to be pushed out into outer space, much like this right here. When we think about solar wind, it comes off the sun at a really fast rate of 400 kilometers per second on average. Of course, it's going to vary in its speed and how far it can travel, so the speed may be faster or slower depending on where you are in space. Solar wind can move much faster over coronal holes and tend to move slower over coronal streamers, which we'll learn about here shortly. So the sun is not uniform in its surface, and the heat factors change in different parts around the surface of the sun. And so that makes solar wind vary from place to place and how strong it can be. So let's talk about what are helmet streamers. I think these are kind of neat. These are large cap-like structures that are found in the corona or the atmosphere of the sun, and they have long pointed beaks like this one right here where the arrow is pointing to. They typically are found above sunspots, and they're very active regions of the sun. Why is this important? Because they form a network of magnetic loops that connect the sunspots and are formed by the action of solar wind. So as the solar wind blows away from the sun, these helmets can actually, streamers, be moved or lost to space. Another phenomena of solar events are called polar plumes. So they happen towards your north and south polar regions of the sun, where we get open magnetic fields that literally pull out polar energy and streams it out. And that's what a polar plume is. So they occur pretty much at your north and south polar regions of the sun, and we get this energy that can be plumed out. Coronal loops are what you see in this diagram right here where the arrow is pointing to it. And this is when you get solar wind or the plasma that we were talking about earlier, and it leaves adioses from the sun's corona. So it's going out, and some of the star's magnetic field carries it into outer space. So this is it can be a very important thing. If you get a huge coronal loop, there's a name for this. Coronal loops influence how our solar wind behaves and interacts with planets. So let's investigate what we call coronal holes. So coronal holes are just, in essence, they're kind of where the magnetic lines at the north and south polar regions of the sun sometimes have a gap. And this is the darkest patches where you see that happen on the surface of the sun. So these regions are important because different parts of the sun do different things for controlling its energy or releasing its energy. An example of that would be a solar plague. These are very bright sections of the sun. For example, right in the illuminated section right here. So what happens is when you get one of these bright areas, they extend outward from the sun's surface. And they're interesting because the solar plagues, they're actually anchored to the surface in the photosphere, and then they extend outwards and kind of go up through the corona. So plagues, the key thing about them is they're the bright sections of the sun's surface. Another important aspect of the sun are sunspots. These are areas that are cooler, not hotter. Some people think that it's just the opposite. But what happens is there are dark patches on the sun's surface that really aren't associated with the polar regions. And these are areas typically where the magnetic fields of the sun tend to be pretty high and strong. And that keeps some of the heat from the sun reaching to its surface. So you can actually see that sunspots are important because they recognize to us in terms of weather, heat, those kinds of things that we monitor from the cosmos. We track sunspots for that very reason. Solar flares are really phenomenal events because what happens is we get an intense burst of radiation that releases, along with the magnetic energy associated with sunspots, out into outer space. They are very active regions of the sun and can wreak a lot of problems and havoc to us on Earth, or if you were in outer space, to electronics. So we do care about solar flares, and I want to show you one that has been done in or measured by NASA so you can kind of see what they look like. As you're seeing NASA's Solar Dynamics Observatory capture this amazing image of a solar flare, you're seeing what's called a coronal mass ejection. And it's really phenomenal because you get the flare, you get the ejection, and this is stuff that's coming out of the energy of the sun. So the sun is not just uniform thing. It is a very dynamic place. Having seen what you saw with solar flares and what we're learned about as coronal mass ejections, this stuff gets into outer space, and this electromagnetic surge, if you want to call that, gets funneled into the cosmos and works its way outward from the sun. And it certainly can reach Earth and other planets. Which leads me to CMEs, or coronal mass ejections. And you just saw how that worked in NASA's captured moment of the sun. And as it does, these eruptions, these expulsions of plasma and magnetic field from the sun's atmosphere, meaning its corona, it's important. Now, the coronal mass ejections don't travel as fast as solar flares, so we care very much about both, but the solar flares can reach Earth faster, and so we have programs to monitor all of these items so we can be prepared for the events that do occur. And now, with electronics being a part of everybody's life, most everyone is aware that there can be disruptions from time to time that are associated with solar releases of energy like solar flares or CMEs. Let's talk about auroras. One of my favorite things that happens because of the ejection of solar magnetic material and solar flares is something that creates this phenomena of beauty. Now, Earth is not the only place it happens. So if you have an atmosphere, a planet, a moon, and it's getting the same kind of energy, the solar magnetic energy, an aurora can happen in other places. So what are they? When we get the particles from solar eruptions like solar flares, CMEs, and they collide with our magnetic field, they enter our atmosphere, and we have a really remarkable thing happen in the thermosphere. We get what I would call the color show of the skies. And if you've not seen an aurora in person, it should be on your bucket list. It is truly phenomenal. I've seen the ones in the northern and the southern hemispheres, and they are not the same. So no aurora is exactly the same. They have some similar properties. So the more common type of aurora that you can see is when the particles come in contact with oxygen and they give off a green and red light appearance like you see on the left side there. And essentially the way we get the auroras is you get the solar eruption, which are the flares and the CMEs, and you get that cosmic energy and magnetic field and all the stuff that's in there, and it comes and collides with our atmospheric areas, primarily around our polar areas of our planet. And so if you get the blue and reddish purple light, that's more rare. I've seen both. They're extraordinarily beautiful. So let's look at a little more about auroras and why they're so important. Borealis, so aurora borealis is what we have we refer to as the northern lights. And they occur sometimes further than just the North Pole. If you get a really just a phenomenal borealis event, you can actually see them in some of the northern states in North America or in the United States. And I have actually been in Montana, lucky enough to see some, certainly in Alaska. And so these are things that I would say, stay tuned. If you visit a place like this, it's worth it to see. The aurora australis is also a type of aurora, and it's found in the southern hemisphere. They call these the southern lights. So I got to go to New Zealand and get to see some of these, and even in Australia. And it was just incredible because having seen the northern lights, now I've seen the southern lights. If I got a chance, any travel I did, this would be something I would go out. And if I was like living in one of these areas, I'd be out in the night sky if we were getting solar flares and the right ingredients to make the amazing northern and southern lights. So you have to understand, we don't get the auroras just magically. They're directly related to the expulsion of sun's magnetic energy and the solar flares and the particles associated with them. And they come in contact with our magnetic field. So if we didn't have a magnetic field, we wouldn't have an aurora. So without getting into too much depth here, we have a magnetic field because we have a solid inner core and we have a liquid outer core that spins around it, which creates a magnetic field. Without it, life on the surface would probably be limited if we even had oceans to the oceans and maybe soil. It would probably be microscopic. So our magnetic field is an essential ingredient for maintaining life. Let's look at another solar event called solar prominences. And sometimes these can be misinterpreted or cross-linked with solar plagues. If you think back to a plague, those are the bright sections. They actually kind of make a cloudy section right on top of the sun's surface. Well, solar prominences are ejections of material that come out. They make a kind of beautiful loop-looking feature. Some prominences can hang out in outer space for several days, just out in the next to the sun where they've released this material, because they are the energy that hangs out in the corona. Remember, the corona is the outer atmosphere of the sun, the stuff that we can't see with our visible eye. So prominences are really special and beautiful. As we shift gears, I would like to talk about the moon because it's our neighbor, an important part of our history. The moon was thought to colliding with the Earth somewhere in its early existence because the Earth was originally a molten state, and it's begun to make a crust in its early existence because the Earth is 4.56 billion years old. At that time, we think the moon was probably about the size of Mars, and it smashed into the Earth. You can imagine the impact and what that did. There's a lot of theories about how that impacted the Earth and the moon. But the term that we use to describe the moon is lunar or luna. And luna is a term that refers to a Latin word used to describe the moon. So the far or backside of the moon was not even known. We had never seen it because this is a tidally locked system to Earth until the Soviets were able to get a spacecraft to go to the backside of the moon and get some images of it. And then we learned, oh my goodness, the backside is very, very different. And it was made of lots of densely cratered sections. We refer to those smooth basins as the lunar mare. The moon is the brightest object that we see in the sky for the Earth from where we are. And the moon does play an important role with that gravitational attraction to Earth. So it kind of keeps our axis, because our axis wobbles and it allows it to kind of stay in its good place. Now, the moon itself is not active in plate tectonics today, but clearly was in geologic past. And it has about a sixth of the gravitational attraction to the surface that we would have on Earth. So if you got to the moon, man, if you were hitting a golf shot, it could go a long way. If you were going to take a step, you could step, and that's why astronomers have to practice the astronauts to be able to appropriately take moonwalks. We do know that the lunar surface is heavily bombarded with craters, and we'll look about that in a little more detail. Don't expect you'll remember the diameter of the moon, but I want to compare it to Earth. Its diameter is 3,460 kilometers, making it smaller but comparable to Earth, and that's an unusual situation for a moon. Its density is about 3.3 times that of water, so it has what we call a pretty low specific gravity. So its crust is super similar to the crust that we see for continental crust on planet Earth. We think it has a small inner iron core. The top or the surface of the moon, again, it's tidally locked, so we see one side of the moon, which is the front side or the near side of the moon, and it spins on its axis. As it does, it can make a full orbit around Earth, but what we're seeing is the front side of that moon. We refer to this process as a synchronous rotation. So when we get there, we're going to take a look and we're going to show you the different sides and what's the features of the moon. So I think history is important here, because in 1969, I was alive and remember landing on the moon, the Apollo 11 mission, and humans taking their first step onto the surface of the moon, putting the first footprints there. Wow, it was such a big deal. My dad is a surgeon, and he was good friends with one of the medical doctors on the team for that monitored the Apollo 11 astronauts. And he was given a piece of a cardiogram of one of the astronauts. I have it at my house. It's all framed and certified. It's a pretty cool thing. And I can just tell you, it's neat. It's just a really important piece of history. But that wasn't the only time that people walked on the moon. In the Apollo 17 mission, that was the last time in 1972 that people walked on the moon. But we have future lunar studies being planned, not just by the United States or NASA, but other space programs. So we didn't just collect all of the knowledge of the moon from people that got there. We've done a lot of remote sensing, satellite work, lots of information that's been gathered together, but we have taken samples from the moon, and that's really where the rubber meets the road in terms of understanding the chemistry of the rocks that are there. And as a geologist, I find that pretty exciting. So we know the highlands crust was made early on in the moon's existence, somewhere around 3.8 to 4.3 billion years ago. So the moon, much like Earth, had a molten surface, it was like a molten sea, and eventually that began to crystallize and harden into the surface that we have today. What's cool is the rocks that we've collected from the moon support hypotheses that it has a similar composition to Earth, which would kind of make sense if it smashed into Earth. It is the result of something we call differentiation. And differentiation is when heavier elements sink towards the center of a planet or a moon, and the lighter elements rise, and lighter in its density is what I mean. So lighter elements that are rich in feldspar did come to the surface, making a plagioclase type surface, which we're going to get to in just a minute and talk to you about what that looks like. Then after we get that crystallized surface, very short after that happened, the moon just got hammered for a period of time by meteorites. And we'll take a look at that time scale in just a second. The oldest lunar rock that's been discovered happened in the Apollo 17 mission, and it's around 4.5 billion years old, likely meteorite or the original crust that was formed on the moon. So you can see their highlands over here, and then the mare down here is the lava fields, and we're going to take a look at both. The highlands are made of very high silica-rich rock, and we refer to that as anorthosites. It's not quite granite in chemistry or diorite, so it's not quite felsic, not quite quite intermediate because there's 4 different classifications of igneous rocks: felsic, intermediate, mafic, and ultramafic. This is in the intermediate to felsic area called anorthosite. So these anorthosites are what make up a lot of the rock chemistry that we see in the highlands, the older rock. The mare, or the stuff that makes up the smooth parts, the lava fields, is my personal favorite because I like lava. And this is made up of mafic basaltic rock. We have the same kind of rock on planet Earth. It's a vesicular basalt, vesicular referring to these things, the little gas cavities. So that means that it was active like Mars and Earth. It had volcanism. We have another rock that's important called breccia. This stuff is formed when you get meteorites that smash into Earth and you have a collision. And the collision sautés, for a better lack of words, literally pulverizes and turns some of the stuff it contacts in with from the meteorite to the surface of whatever it touches, makes a glass-like beads and glass-like morphology and crystals from the impact itself. So we get an impact-related shocked quartz is what we call it. And in these breccias that we find them in both the highlands and the lowlands, which is important to note. So the highlands are the bright, densely cratered regions of the moon, and they make up a majority of the moon's surface. And that's the stuff over here. Certainly the backside of the moon is covered with it. Remember that highlands is older, and it's also filled with lots of craters. No craters are the same on the surface of the moon, but there are some themes along with them. Some craters are very round with a very steep crater wall at the top. Some have slumps that come into them. Some have bright crater rays like you see right here, which is ejecta from the actual meteorite collision. So when we have a meteorite collision, we can get what's called inverted strata or strata. And inverted strata is where you get older rock layers that get thrusted on top of younger ones. And in the impact itself, you're going to displace what was there originally on the surface of the moon. And then the breakup of the meteorite will also explode. And you can get some of it that stays in the crater and then gets fallen out on the side. So that's called an ejecta blanket. Most all lunar craters that are 30 kilometers or greater on the moon's surface have kind of this flat floor. Not the case for the younger ones that are smaller. The smaller craters have these swirl-like features in them, which is thought to be ejecta and mass wasting slumpage of materials that come into more of the floors. Younger craters tend to have blocks that fall because they don't quite make it out as ejecta, and they break and they toss them back into and along the crater rims. The lunar mare are the exciting parts of the moon to me because this is where all the lava flows are. So these are the dark sections of the moon, and it is heavily covered with lava. So all the lowlands that are really smooth areas covered by lava flows, they're much younger than the highlands. That brings us into the geologic time scale, and there is one that was put together for the lunar existence of what we think happened. And this was put together in the 60s, 1962, by Shoemaker and Hartmann. They're very important scientists that look at the cosmos in terms of the history of the moon. So we're going to look at these 5 periods, and we're going to start with the earliest, called the pre-Nectarian period. This is the oldest period, ranging from right at the formation of the solar system, 4.6 billion, to right around 3.92 billion years ago. So this is when the moon's cooling off. It's beginning to have intense bombardment of craters, so from meteorites. So this is down here, right in this section. And we get a lot of our big basins formed there. The Nectarian period's named after the formation of the Nectaris Basin, which occurred somewhere between 3.85 billion to 3.92 billion years, right in this sliver of time right here. The Imbrian Basin period's my personal favorite because that's when all the lava was made predominantly. So that puts us right in here. And we get all these massive flood basalts, which are flood waters. The basalts flowed freely for tens and tens of kilometers away from their volcanic resources. This happened 3.85 billion years ago to 3.16 billion years ago. The Eratosthenes period is the next one, and this is a period when we created the crater by which it's named. These craters tend to have terraced walls that have very circular floors, distinctive sets of secondary craters from being bombarded again. But the key thing is the ejecta outside of them is not ray-like. It's very dark. So this is an important time in a very large stretch of 3.16 billion years to about 1.1 billion years of geologic history. The youngest period is Copernicus period, and this is named after the Copernicus crater on the moon. This is where we start to see craters that have the really bright rays on them, and these bright rays are younger than any other features on the moon. So this particular period lasts from about 1.1 billion all the way to current time. Which brings me to the lunar phases of the moon. And the lunar phases, when we talk about them, we're going to make a reference point that they're in the northern hemisphere because everything's opposite in the southern hemisphere. And the moon orbits in a counterclockwise or eastward direction. So what we see from moon being dark at new moon phase, we start seeing things happen in the northern hemisphere from the right side until we get to full moon, and then it slowly moves to the left side. So we're going to take a look at each phase. There are 8 phases of the moon, and you need to know all 8 of them. And we have a different view of the moon in what we call our moon cycles based on where it's located and its travel path around the globe. So we're going to start with the term waxing means growing. So the first phase we see in the North America side starts at the right. We get a little sliver called a waxing crescent, and the moon is partially illuminated. And it'd be opposite, obviously, in the southern hemisphere. When you get to first quarter, this is where we made a quarter of the way of the journey of the moon through its monthly process. And this is where you see half of the moon illuminated. I like the first quarter phase. I think it's cool. I also like gibbous phase, and especially waxing gibbous. This is where the moon is between half moon and full moon, and it's still growing and getting larger. When we make it to full moon, everybody loves the full moon phase because you see the full side of the moon, the near side of the moon, and it's fully illuminated. Sometimes you might hear that we're in a blue moon phase. That's actually where you have 2 full moons in a month cycle. If you have a red moon, that's typically associated with solar eclipses where the moon can appear to be blood red. There's things called harvest moons, all related to proximity of the moon to the earth and timing. When we start to see less of the moon in the northern hemisphere, everything's moving to the left. So a waning gibbous is where you have more than half of the moon illuminated, but not at full moon, and it's getting smaller. So the left-hand side version of gibbous. At last quarter, this is where we get the 3/4 mark of the moon's journey, and we have 1/2 of the moon illuminated. A key point on this one is the moon is high in the sky when the sun rises in the morning. High in the sky at sunrise. Different when you get to waning crescent, where you get that little sliver on the left side. That's where the moon rises just before dawn, and it's partially illuminated. When we make it to new moon phase, hey, you're not seeing it in the sky. It's dark. So new moon refers to dark. So remember, there are 8 phases of the moon, important. The lunar phases are what we see each month, and there's certain descriptions of what we call a lunar month. So I'd like to quickly go over that. Sidereal months are what we call the true period of the month's revolution around the Earth, and it takes 27.3 days to complete. So this is an important description of what we think the true moon's revolution is as scientists. Synodic months are the moon phases of the month, and this is the mean length of time that it takes for the moon to do its cycle. So it's slightly longer, actually 2.21 days longer than the other month that we have, the true cycle of the month. So it's 29.53 days. In addition to the phases of the moon, there's a few more terms that are important for understanding our relationship that the Earth has with the moon, and one is the distance between those two bodies. When the moon is closest to planet Earth, we call that a point of perigee, and that can make the moon appear much larger. So if we have a period of time where, like a harvest moon and it's full moon cycle and we're at perigee, that moon's going to look exceptionally large. Apogee is the point where the moon is farthest away from the Earth. So it is smaller in appearance. And I think that's important, especially if we're going to be covering eclipses, how those can affect what we see in the sky. So a good way to remember the two from one another, apogee is far away. So A for away, apogee, and perigee for that point, that focal point being right close to the Earth. That was what I remember as perigee. Lunar eclipses occur when the moon actually moves into the shadow of the Earth. And when doing so, this can only happen at one phase of the moon, which is during full moon, for this type of eclipse to occur. Certain kinds of lunar eclipses can actually produce a reddish color based on the shadow and where it is in proximity in the shadow of the Earth. So when we have a total lunar eclipse, that occurs when the moon and the sun are on opposite sides of the Earth. And so basically that shadow just totally eclipses that portion of it. So the partial lunar eclipse only happens when a part of the Earth's shadow covers the moon. So you're looking at varieties in the illustration below of what a full lunar eclipse would be over here on the left, and then you can see the different colors, which happens to be the shadow color of the kind of what the sun is reflecting off there of the shadows that we're seeing on Earth, the different partial lunar eclipses. During a partial lunar eclipse, we only have a portion of that moon that gets covered by the shadow of the Earth. So it can look like there's been a bite of it taken out of the lunar surface. So like right here, this is where that moon is, and our shadow is casting upon it. So the more of the moon that's covering this section, the more sliver that you'll get of a partial lunar eclipse. But that red illumination from the sun can actually help change the color of the moon during a lunar eclipse. Now, solar eclipses are pretty cool. And certainly a total solar eclipse is kind of like a lifetime moment. When the moon is at new moon phase, so we're not seeing any of the face of the moon, and it passes directly between the Earth and the sun, this is what we call a total solar eclipse. So anytime we're dealing with a solar eclipse, the moon is in between Earth and the sun. In your lunar eclipse, it's the shadow of the Earth that is causing the eclipse. So make sure you get that part clear in your mind. So during a total solar eclipse, what we have is there's a temporary blockage of sun. We can only have solar eclipses during the day. And if you are one of those localities in which you can see a total solar eclipse because the moon's shadow completely covers the sun, then you are in a point of location geographically referred to as the path of totality. This makes these locations exceptionally attractive for people who want to see a total solar eclipse. For example, in April 2024, a total solar eclipse will come right through the strip of Central Texas on up through parts of North America. In fact, right where the college is located, this eclipse will be able to be viewed. So it is a very high tourist destination. So other parts of the world that can see the eclipse on the same day, their location, if they're not in the path of totality, they won't see the total solar eclipse. So wherever a total solar eclipse occurs on the planet, that is the place where the entire moon at new moon phase blocks out that sun. Another type of solar eclipse is referred to as an annular solar eclipse. These are so interesting. When the moon moves between the sun and the earth, and it's at its farthest point, apogee, we can see something remarkable, and that's called an annular solar eclipse, because the moon ends up being this dark, dark surface that's sitting right on top of the sun. And you still get a rim around the outside. That is your annular eclipse. So in a total solar eclipse, if you're in that path of totality, you wouldn't be seeing the sun at all for just a brief few minutes, or however long that eclipse section lasts. And then as it moves off, you would be able to see portions of the sun until the eclipse is completely gone. So in an annular solar eclipse, again, all solar eclipses happen during the day, not at night. But an annular eclipse is really interesting because it makes this distinctive orange rim around the outside of it. And I just really like annular solar eclipses for that reason. A partial solar eclipse, much like a partial lunar eclipse, looks like there's been a bite taken out of the sun. So here's what happens. When the moon passes between the earth and the sun, but the sun, moon, and earth are not perfectly lined up in a row, only part of the sun will be blocked out or covered. And this makes it look like a bite's been taken out of the sun. So remember the partial lunar eclipse, it looks like part of the moon's been taken away. In this case, part of the sun's been taken away simply because of the moon and the alignment between it and the sun and the earth. So during the solar eclipse, the moon is just sitting right in between the earth and the sun. So it matters if we're at apogee, perigee. All of these things have factors of what we can see in a different types of solar eclipses. During a total or annular solar eclipse, if you are outside the area covered by the moon's inner shadow, you'll only see a partial solar eclipse. And so what most people end up seeing during total eclipses is this right here. So if you're lucky enough to be in a place and you can get a viewing spot that's optimal, and of course the sky is clear, you definitely want to be in the path of totality in order to see your total solar eclipse, or else you'll see something like this. There's still exceptionally remarkable opportunities, but nothing like a total eclipse or an annular eclipse. A hybrid solar eclipse is something unique because since our Earth's surface is curved, an eclipse can shift between annular and total as the moon's shadow moves across the globe. And when this happens, we can get a hybrid solar eclipse. And they're really, really cool. Regardless of what kind of solar eclipse you're looking at, for that matter, any eclipse, you need to make sure that you have proper viewing glasses on, which are not sunglasses. There are certain types of glasses made for viewing the sun in an eclipse so you don't damage your eyes. So please take good care in making sure you've purchased what you need to protect your eyes, because even when you're at that total solar eclipse, as soon as that starts to move and everything shifts a bit, you're going to get that immediate radiation into your eyes. So let's apply what you know. You've learned about our remarkable sun. Nuclear fission is what makes that work. So at some point, nuclear fission is going to die down in the sun, or it's going to slowly change, and eventually we'll end up in that red giant phase. And I want you to make the connection, what happens after red giant stage, of the different star stages you learned about in our last lesson. Then we can take a little lesson from the moon, our closest neighbor. We can look at those rocks that have been analyzed in studies that are lunar rocks, and we can see that there's been different geologic histories for the moon. So it was once tectonically active. We know one of our neighbors in space is also, or was also tectonically active, Mars. And we need to recognize that Earth has lessons to be learned from some of our celestial body neighbors. It won't always hold the same type of volcanism that we have today. In fact, over geologic history, it's changed. And the moon is evidence that plate tectonics changes over time. It has none today. But it certainly did, since we have those massive lava fields that we were talking about made out of basaltic lava. And that the actual crust, the older continental crust, is made of something very similar to what we see on parts and lots of the crust of the Earth, continental crust that is. But don't forget that the moon has extraterrestrial gifts, which are the impact craters. Earth has them too. So everywhere we go, we need to be thinking about what is happening in the cosmos, what has happened, and how can it affect humans. So the study of astronomy and the cosmos is important to us. So learning about outer space and our neighbors can tell us a lot about what's happening here on Earth, what has happened, and what could happen in the future. And hopefully, as we move forward in our journey into the cosmos, we'll learn even more than we know, even about our closest neighbor, the moon. So I hope you'll take a moment just to look at the night sky, take a look at the sunrises when you're seeing different phases of the moon, especially at the waning phases. And you'll notice that our moon changes during our months, what the 2 cycles of the months are that we talk about for the moon, what apogee and perigee means, the different terms that you learned about. And I do want you to take a step back and look at that geologic timescale that we investigated for the moon's history and realize it's different from planet Earth's. While the moon is similar in age, we don't have nearly the wealth of geology there that we do here. It's not just because we haven't been there. It's because our plate tectonics continues and the moon's has stopped. Also, compare the two, thinking about the gravitational pull, thinking about the atmosphere that Earth has versus what moon doesn't have, and why the surface of the moon looks so different from Earth, and how that atmosphere and our gravitational pool that we have, our field that we have on Earth, is so vitally important for maintaining life as we know it. So in our next lesson, we'll be investigating the planets in our solar system and beyond the planets that we call a belt of features that I want you to learn about. So stay tuned for that, and we'll also investigate some of the research and exploration that is happening for us to learn what we know and what we don't know about the cosmos. Thank you. Bye.